The mole. Okay, we've already spoken about the fact that atoms are very, very, very small. In fact, if every single person in the world was the size of an atom, the entire human race would fit on the head of a pin, and there'd be room for lots, lots, lots more. Okay, because they're small, they've got a really small mass. For example, carbon's mass for one atom is 2 by 10 to the negative 23 grams. That is that small. This is difficult to measure. It's difficult to use in calculations. But we don't need to know an element's exact mass because we can work out that mass relative to other elements. And we've already discussed relative isotopic mass, which is the mass of one atom of that isotope relative to the mass of one atom of carbon-12, which equals 12 units exactly. So relative isotopic mass, from there we can work out relative atomic mass, and from there we can work out relative formula or molecular mass. If you don't know any of this, please go back and have a look at my other videos on relative isotopic mass. I will go and explain these concepts. You need to know this stuff to continue on with this video. So scientists can count using a convenient quantity of atoms and molecules so that they can weigh stuff, so that they can work in the laboratory, and so that they can use in calculations. So it's counting using a convenient quantity, and this quantity is the mole. And all it is a counting quantity. The mole, definition: the amount of substance which contains as many elementary particles as there are atoms in precisely 12 grams of the carbon-12 isotope. Okay, that's a mouthful. Basically what that is saying is that 1 mole is equal to the number of atoms in 12 grams of carbon-12. Remember, carbon-12 is our most commonly occurring isotope, and this is why we use carbon-12. That's how we work out relative isotopic mass based on carbon-12, and here the mole is the number of atoms in 12 grams of carbon. And this is equal to a quantity which is 6.02 by 10 to the 23rd. So this is an enormously large number. So the same way that eggs are counted in dozens, where 1 dozen equals 12, chemists count in moles, which 1 mole equals 6.02 by 10 to the 23rd. It's just a counting quantity. So, Avogadro's number. Avogadro was the guy that came up with all of this, and he's so famous that he gets his own number that we use all the time. So this number is the number of elementary particles in 1 mole, and it is equal to 6.02 by 10 to the 23rd. So this is Avogadro's constant, or Avogadro's number. 1 mole of particles contains 6.02 by 10 to the 23rd particles. And it doesn't matter what type of particle it is, 1 mole always has 6.02 by 10 to the 23rd of those particles. So, just like 1 dozen eggs equals 12 eggs, 1 mole of eggs would be equal to 6.02 by 10 to the 23rd eggs. That's a lot of eggs. Let's have a look at this. 1 mole of dogs equals 6.02 by 10 to the 23rd dogs. 1 mole of elephants equals 6.02 by 10 to the 23rd elephants. 1 mole of ants equals 6.02 by 10 to the 23rd ants. A mole of ducks. A mole of ducks contains 6.02 by 10 to the 23rd ducks. So it doesn't matter what we are dealing in, 1 mole of substance, whether it's a chemical, whether it's an ant, whether it's a fly, will always have 6.02 by 10 to the 23rd of that particle. So how big is this mole? Well, here's an example that if an atom was the size of a grain of sand, 1 mole of sand grains would cover the entire land mass of Australia to a depth of 2 meters. So it's a lot of particles. 6.02 by 10 to the 23rd. 1 mole equals the number of particles, which is 6.02 by 10 to the 23rd. It is not equal to something's mass. If we have a look at a mole of elephants, which is 6.02 by 10 to the 23rd elephants, these elephants are going to weigh a lot more than a mole of ants will. There's still 6.02 by 10 to the 23rd of each of these, but a mole of elephants is going to weigh hundreds of times more than one mole of ants. And this is important in chemistry as well. When you have a mole of carbon here, 1 mole of carbon-12 equals 12 grams exactly, because this is what it's based on. 1 mole of carbon-12 equals 12 grams exactly. Based on relative mass, 1 mole of copper then is going to weigh 63.5 grams, because copper is a much bigger atom. It has a higher relative atomic mass than copper does. But it will still have the same number of atoms if there's 6.02 by 10 to the 23rd atoms. But remember, copper is bigger, so it will weigh more than carbon will. Here's some examples of 1 mole of several common substances. So we've got table salt. That's 1 mole of table salt particles. We've got a mole of sodium chloride, NaCl. We've got 1 mole of carbon, 1 mole of copper, and this is 1 mole of helium here in this balloon. So you can see how they're different quantities. The number of atoms in all of those, though, is the same. Here's another example. We've got a mole of mercury, a mole of zinc, a mole of silicon, aluminium, a mole of sulfur, and a mole of bromine. Again, they are different amounts by weight, but it's the same number of particles. Each one of those contains 6.02 by 10 to the 23rd atoms of those substances, but they will weigh different amounts based on their different relative atomic masses. So, how do we use this in calculations? Let's look at this side here first. If I was to give you a number of eggs, for instance 24 eggs, and ask you how many dozen there were, you would simply divide by 12 and tell me that there was 2 dozen. Or, if I was to tell you that there was 3 dozen eggs, you would multiply by 12 to let me know that there was 36 eggs. Same thing when it comes to the moles. So, if there's a number of particles here, all you need to do to tell me how many mole that is divide by 6.02 by 10 to the 23rd, which is Avogadro's constant. And that will give you the number of moles. Or in the other case, if I tell you that there are 2 or 3 moles of a substance, to find out how many particles there are, you multiply by 6.02 by 10 to the 23rd, which will tell you the number of particles. What I suggest you do at the start is just write down this egg example here, and then underneath write down the number of particles and the number of moles. You won't get confused this way. The other thing to look out for when you're working this out is the number of particles is always going to be a big number, whereas the number of moles is going to be a small number. So number of particles would be something by 10 to the 23rd or by 10 to the 22nd, whereas the number of moles is always going to be 1.2 or 0.3 or 3.6. So we can work out the number of moles of a substance, which equals the number of particles divided by 6.02 by 10 to the 23rd. So the number of particles divided by 6.02 by 10 to the 23rd will give us the number of moles of a substance. Or the other way around, the number of particles of X equals the number of mole of X times Avogadro's constant. So if I know how many mole there are, and I multiply by Avogadro's constant, I'll find out the number of particles of X. So let's have a look at an example question. How many carbon atoms are present in 5 moles of sucrose? And we've been given the molecular formula of sucrose, which has 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms. How many atoms are present altogether? And part C, how many moles of carbon atoms are present altogether? So let's look at the first part of the question. How many carbon atoms are present in 5 mole of sucrose? The first thing we need to do is write down what is the question asking us. It's asking us in 5 moles of sucrose, how many moles of carbon are present? So if we have a look at the sucrose molecule, 1 mole of sucrose, each mole contains how many carbon atoms? It contains 12 carbon atoms. So 1 mole of sucrose must be equal to 12 mole of carbon. So to work out the total number of mole of carbon, we look at this ratio of sucrose to carbon. This ratio here we can use in chemistry, and we use the unknown over known. So what we're looking for here is the number of mole of carbon. So our unknown is carbon, so it's 12, divided by what we do know, which is the 5 mole of sucrose, and the ratio is 1. So we put 12 over 1, because this is our unknown to known ratio, multiplied by the information of our known, and we get an answer of 60 mole. Now you can use any form of ratio to work this out, but this is the way it's done in chemistry. Some teachers might use want over got instead of unknown over known. So we still need to work out how many carbon atoms. This is the number of mole of carbon atoms. Remember, mole is a counting tool. So to work out the number of carbon atoms, we need to multiply the number of mole of carbon by Avogadro's constant. We've just calculated the number of mole of carbon here, which is 60. Avogadro's constant is 6.02 by 10 to the 23rd. So we get an answer of 3.6 by 10 to the 25th atoms altogether. Notice the units, and always double check that that's what the question's asking you for. If the question asks for atoms, you must answer the question in atoms. You can work out the question the other way around. So if you know the number of moles of sucrose, you can multiply by 6.02 by 10 to the 23rd to give you the number of molecules of sucrose. You can then multiply that by 12 to give you the number of carbon atoms present. Either way will give you the right answer. I like to multiply by the ratio first so that I don't forget to do that. Question B is asking how many total atoms or atoms altogether are present in that 5 mole of sucrose. So again, write down what the question's asking you. 5 mole of sucrose contains how many mole of atoms? If we have a look, 1 mole of sucrose contains a total number of 12 plus 22 plus 11, which equals 45 atoms altogether. Every mole of sucrose is made up of 45 atoms. So 1 mole of sucrose must equal 45 mole of atoms. Again, working out the number of mole of atoms, you look at this ratio of unknown, which is what we're trying to work out. So it's 45 divided by 1 times the information we know. So it's 45 over 1 times 5, which gives us a total number of 225 mole of atoms in total. We need to work out how many atoms. The total number of atoms is the number of mole multiplied by Avogadro's, which will give us 225 multiplied by 6.02 by 10 to the 23rd, which equals 1.4 by 10 to the 26 atoms. So the last part of the question is how many moles of carbon atoms are present altogether. We have already worked this out in part A, but I'd like to show you how to go backwards. So the number of carbon atoms we calculated was 3.6 by 10 to the 25. To calculate the number of mole, we divide the number of atoms divided by Avogadro's constant, which of course is 6.02 by 10 to the 23rd. So our answer up here, number of carbon atoms, which is 3.6 by 10 to the 25, divided by 6.02 by 10 to the 23rd, which equals 60 mole of carbon atoms. As I said, always check that your answer equals your question. So, to go backwards from different things, if we know the number of moles of sucrose, if we multiply by 22, we have the number of mole of hydrogen atoms. If we multiply by 12, we have the number of mole of carbon atoms. By 11, we get the number of mole of oxygen atoms. And of course, as we've just done by 45, we get the number of mole of atoms altogether. This is question 18 in your notes. I'd like you to pause the video, have a go, and I'll pop those answers up for you. So question A, you should have gotten 1.8 by 10 to the 24th atoms. Part B, 3.61 by 10 to the 24 molecules. And part C, 3 moles. I'm going to put the work solutions to those up now. If you've gotten the correct answers to those, you don't need to watch any more of the video because it's just those work solutions to follow. Question 18A in your booklet. How many atoms are present in 3 moles of lithium? So, each mole of lithium has to contain 6.02 by 10 to the 23rd atoms of lithium. So, number of lithium atoms equals number of mole of lithium times Avogadro's constant is 3 times 6.02 by 10 to the 23rd. So it'll equal 1.81 by 10 to the 24th atoms. If you're talking in atoms or molecules, this is always going to be a big number with 10 to the 23rd or 10 to the 24th after it. Okay, it's going to be a massive number, and this is why we use moles. Let's have a little look at 18B. How many molecules are present in 6 moles of H2O? Remember, 1 mole of H2O will contain 6.02 by 10 to the 23rd molecules of H2O. So we can work it out. Number of H2O molecules equals the number of mole of H2O times Avogadro's number, which is 6 times 6.02 by 10 to the 23rd, and that equals 3.61 by 10 to the 24th molecules of water. Each mole of water contains 6.02 by 10 to the 23rd molecules of H2O. Let's have a look at 18C. How many moles of carbon dioxide in 1.806 by 10 to the 24th molecules of carbon dioxide? Remember, 1 mole of carbon dioxide contains 6.02 by 10 to the 23rd molecules of carbon dioxide. So we can work out the number of moles of carbon dioxide by the number of molecules divided by Avogadro's number. So that's 1.806 by 10 to the 24th divided by Avogadro's constant. And that tells us that there's 3 moles. In other words, 3 times 6.02 by 10 to the 23rd molecules of carbon dioxide.